My name's Sasha Kasky. I'm the CTO and co-founder for Casisto, and I'm speaking to you today from New York City, New York. I'm really excited to talk to you a little bit about the future of conversational AI for Chatbot Africa Summit. Unfortunately, I can't be there in person this year, but hopefully next year, if we do this again, we'll get to do this face to face and get to know each other, which would be really exciting, at least to me. Last year, we spoke a bit about the future of conversational AI, but we took a broad view of it. We wanted to talk about AI, how AI is affecting the industry, and then we focused a bit on sort of NLU and natural language processing and what some of the trends there were. Well, I figure this time around, I will take you a little bit deeper on natural language processing and focus on the research of today that's affecting the systems of tomorrow in the near future. So I'm not going to be talking about sentient AIs, although you'll hear that word every once in a while coming out from me. And instead, we're going to focus a lot on aspects of what does it take, what are the aspects of AI that is in research today that's affecting systems of today and of the near term. Before we do that, just to make sure, I'm sure everybody in the room is an expert in artificial intelligence, but I always like to go through a brief history to see where we are. So the question was originally posed back in 1950 by Alan Turing, considered by many the father of AI and computing. Can machines learn? And he posed it in a very specific way. He posed the Turing problem, which I won't get into now, which basically tries to evaluate has humans trying to evaluate a system to decide if it's an AI or another person. There's an entire prize that goes on today called the Turing Award and a competition along with it. The term itself, artificial intelligence, was first coined or used in Dartmouth College back in 1958. As you can see, AI is an older discipline than I am, and I'm pretty old. But the concepts of AI, the mathematics of AI is much older than even this. In the beginning, AI and the work that we did was really limited by hardware. It was really thought of as a search problem. All you need to do is you need to lay out all the possibilities, and you can think of a game of chess, for example. Given the board today, what are all the possible moves that I could ever do and all the reactive moves from that? And you can just imagine this huge tree growing from that. And then the best AI is the one who could travel through that large network and find the best path to a checkmate. Well, that dominated roughly the 1950s all the way through the 90s. What happened in the 90s is that computers started getting fast, and they started getting fast, real fast. In fact, Moore's laws told us that the number of transistors and resistors on a chip doubles every 24 months. Well, turns out that was nothing compared to what the cloud did to computing, because all of a sudden, it didn't matter. It didn't only matter what chip could do. Now, all the chips in the world can be working together to solve a new problem. So the cloud computing, distributed computing, massive amounts of storage and data have really allowed the field of AI to completely revolutionize. Things that were impossible before, now you do for breakfast, and we're learning and every day, and the field continues to evolve. At its base, the field of AI is broken into two parts, the rationalists and the empiricists. Rationalists are those that believe that you need to teach an AI, you teach it rules, you teach it graphs, you teach it your knowledge of the world, you transfer that to an AI, much like how we teach our children or how we ourselves learn when we go to school or university or take a course online or read an article. Then there are the empiricists who believe that the AI should really learn from observing. You shouldn't have to go and tell the AI that this is a rule or that is a rule. It should be able to observe the world much in the same way that we do as well and learn from that. It should be able to learn to speak by listening to other people speak. It should be able to learn how to write and read and to be able to infer by just observing. Well, much like us, most AI systems that are successfully rolled out today use a mixture of both these methods. It turns out that, I think, and just like we are in the examples that I've used, it creates the most impactful solutions are built from a mixture of empirical and rational AI solutions. Enough about that. Let's talk a little bit about the areas of R&D. When you're focusing on conversational AI, which is what I've spent most of all of my career doing, there are three main pillars that any interactive AI system needs to be able to do. First, it needs to be able to understand, right? You say something to the AI, it needs to be able to transform that into something that it can comprehend. Once it comprehends that, it needs to be able to act on that. And that's called the reasoning. So it's going to do something, ask another question, some calculations. Once it decides what it wants, once it's done its thing and it decides it wants to speak back to you, it needs to communicate back to you in the language that you understand. After all, you don't understand bits, or most of us don't. So it's going to generate that concept into something that we as humans understand. So the focus of today, we're going to talk a little bit about language models and how the large language models have really helped us improve the field and changes. And I'll show a few examples, simple examples that hopefully help you create an emotional connection with some of these advances. Let's start with the basics. So when everybody leaves today, you're going to be a data scientist. Not only that, a natural language data scientist. So what is a language model? So language model, short for LM, is a statistical model that estimates the probability of words. So for example, which of these words is the most probable? The or amyotrophic? Okay, so I guess you thought the, because that's what I would guess, because the reality is, without thinking about it, I don't even know what amyotrophic means. However, if we put this sentence and we ask you to say, what is the most probable word to go into that specific spot, right? Well, you wouldn't say the lateral sclerosis, but most likely you would guess the with amyotrophic lateral sclerosis, ALS. So that gives you an idea of what a language model does. It's really looking at predicting which word is most likely given a context. If there's no context, it will predict it. If there's a specific context, it will predict it within that context, much like we did. Well, what is a large language model? A large language model, when we talk about large, it really means two things. It means it has many parameters, and it means it's trained on a large data set. It uses neural net technology, all of them, in fact, and it represents its words, and often you'll hear people talk about as tokens because sometimes they're sub-word units, as vectors of numbers. And there are many different architectures, and I'll show you some of them as we go through some of the examples of the common language models that are out there. So for example, the word I can be represented by the vector that you're seeing over there. The word saw is represented by a different vector. These vectors are called word embeddings, and the words that appear in similar contexts have similar embeddings. So the architectures, and that architecture is a fancy word for looking at the different stages and the different types. For example, using a feed forward, a multi-head attention, a masked multi-head with attention. Are you using an entire paragraph, an entire document? Are you looking only at a sentence? There are lots of how are you masking your words? The different architectures will allow the AI to learn different properties. And the benefit of these large language models is that what they learn can actually be used in a lot of different applications. So you take the same language model, so for example, Bert, which came out in 2019, and was trained on about 340 million parameters and 16 gigabytes of data. And with that same language model, you can build a system that translates from one language to another. You can build a system that searches, that generates, that understands, that answers questions. You can build so many different systems with a simple one language model that was trained on broad data. Furthermore, if you take that large language model and you fine tune it for your specific problem, you can get even more fantastic results. But as you can see, in a very, very short time, we went from 340 million parameters to almost 175 billion parameters in GPT-3, which is one that most of you have probably heard of, to all the way to 1.57 trillion parameters in Switch C, which is one of the latest large language models published, which was trained on 745 gigabytes of data. So it's a significant, very significant order of magnitude increase in both the data and the number of parameters. And the results are impactful. How impactful? Well, you may remember when GPT-3 came out, both 2 and 3 got a lot of media coverage, and folks are wondering, have we finally reached the sentient AI? Is AI finally going to start, revolutioning the world? Well, the reality is AI is already revolutionizing the world today, but that's a conversation for another day when we are in person. The reality is that some of the headlines that came out says this AI is so good at writing that its creators won't even let you use it. This is going to completely revolutionize artificial intelligence. The next word? Oh my goodness. How do you know a human wrote this? In fact, often you cannot tell. OpenAI's new language generator is shockingly good and completely mindless. This buzzy new AI can make human-sounding recipes, but they still taste gross. They probably do taste gross, but they will read beautifully. Well, what can these large LMs do? Well, I can show you an example of a system that we built here at Casisto in our labs. So we have a prototype that we have built that does question and answering. So basically you can point our chatbot to any website and ask questions, and it will process that website and give you answers. And part of that work, we used one of the very large language models to do natural language generation or text generation. So when our system would return something like the late fee is $100 for outstanding balances above $200, when we sent it to the rewriter, what would come out of that is the late fee for this card is $100 for any outstanding balances above $200. And the only inputs that go into this are the original question asked and the text that our system extracted from the concept. And you can see that these are, they're really, in my opinion, great rewrites. I mean, I would much rather hear, no, this is a free service. I mean, I would rather hear there's no cost to establish a standing instruction than no, this is a free service. Or the late payment fee on a student loan is $30 on any overdue amount after the first of every month versus the late payment fee $30 on overdue amount after the first of every month. And there you go. So that's an example of how LLMs can be used in text generation, the type of impact that it can have. Actually, I didn't even read the best example of all, which is the one around annual fees, but you get to see them. You're probably a faster reader than I am. Another field that I believe has been impacting the field significantly in both search and question and answering and conversational systems are financial knowledge graphs, or knowledge graphs in general. So the ability to learn knowledge graphs from data, to build knowledge graphs from knowledge, or to have knowledge graphs that are mixed, learn, and build, really allows us to make up for a lot of the weaknesses that may occur from the purely empirical systems. So a knowledge graph you can think of as a rational, it's more of the, falls more under the rationalism. I feel even if it's learned, unless it is learned, it is completely learned, right? But in these cases, this gives us an ability to come in, and we know this is the case. We know deposit accounts. These accounts are all deposit accounts, and only this account over here actually is interest bearing. And loan accounts are, these other types of accounts are all loan accounts, and they have their own specific properties, even though they all share this parent ancestor who is an account. So how does this get used? Well, let's show you a few examples, right? You could ask a question, what's the available balance on my credit card? And the system can come back, our system, for example, the available credit of your credit card is $6,800. Notice, and it's very discreet and slight, that it changed balance to credit, because the reality is credit cards don't really have available balance, but they do have available credit. They do have a balance, which is how much you owe. So this type of distinctions are still very difficult to learn from just the data. And a little human help from a knowledge graph can make a huge difference. So we type the same sentence into another financial bot out there, and this is what it came back to. And it says, we offer 2 checking accounts, cash back, debit, and so on and so forth. And without the usage of knowledge graph, our system would have made the same mistake. Another example could be, what's a payment due date on my checking account? Well, checking accounts aren't loan accounts. They don't have due dates. And so this is an answer over here. But on the left-hand side, when we ask this to another system, and again, this would have happened to us in the past, the system can't really understand it. It depends on a lot, how the system was built, obviously, for it to come back and give you that response. Anyway, I had a great time speaking to you today a little bit about AI and the future of AI and how AI is impacting natural language processing and conversational systems. If you would like to have a further conversation with me, please reach out to me. You can find me at sasha@casisto.com. If you'd like to learn more about Casisto and our company, please reach out to us at sales@casisto.com. Have a great day, and I look forward to answering your questions.